because the matrix is symmetrical. Now let's check. You see? Now I move to here. Do you understand what I'm talking? Okay. So it is very easy. You just take a look. Number 7, and then using that mapping from Professor V.B. Kumar, you know number 7 will move to row 5, column 6. And then you can apply that idea for every non-zero. Like for example, just one more test. Can somebody pick up another value for me? Any non-zero, I don't care. Let's say 110. Oh, let's say, how about 66? Can you tell me 66, or what is the location in the old system? Row 4, column 4. Okay. But row 4, column 4 in the old system means row 3, column 3 in the new system. So what it means is 66 will go to row 3, column 3 of the new system. And that's exactly here. See? Do you understand so far? Now, so far you know how to obtain this matrix A star using I-perm from Professor V.B. Kumar. Alright? Is that right? So, you notice you see what it does is, every non-zero that you have in the original system, they move to the new place. Okay? Now, next question. How do you figure out this guy? Let me give you an example. Suppose in the old system, the value B here, let's say is, I just make it up, 1.28 minus 6.0 minus 3.5, whatever. Okay? That is vector B. Now, if you understand, tell me, this value, 1.28, it will be in which location here? Yeah, this is at row 1, right? The location is row 1 of the old system. According to here, see row 1 in the old system, row 1 in the old system now become row 6. So that means 128, 1, 2, 3, 4, 5, 6 now become right here. Do you understand? So now I hope you understand very clearly. If you know A, matrix A, you know vector B, and if you know this information, then you can construct this matrix A star and this vector B star. Do you agree? Now, since you know A star and B star, now you can apply the Cholesky. Step 1, step 2, step 3. Don't apply the Cholesky on the original system. Why? I tell you why. If you apply the Cholesky in the original system, you have 6 non-zero field-in term F. But look at something very beautiful. See, in a new system, all of those non-zero remain 0. The only thing you have only non-zero here. Do you understand or not? Let me tell you why. Can somebody tell me why this guy become non-zero? What is this location? Row 4, column 6. So what is the summation of the product? It will be based on column 6 and column 4. Remember? You see? No, be careful. Don't say 1, 2. It will be a new value of 1. Because this value 1 may become something else. Remember? This one may become 1.39. It could become, but it's non-zero anyway. So, this is row 4, column 6, right? So, you look column 6, look column 4. Non-zero, this time this, non-zero. Plus, this time this, still 0. This time this 0, but this guy non-zero. And that's why you have a fill-in. You see, that is the only non-zero fill-in term. So instead of having 6 extra non-zero, by doing this, you only have 1 extra. And that means what? You will save the computer memory and you will save computer time. Is that clear? So, see, because anybody can solve AX equal to B. We even know that even in high school. But when you look at the more detail, you need to understand a lot of secret in there. Okay? Is that very clear? Now, I'm going to show you a real life application, engineering application, that will show you the advantage of applying the so-called Professor V.V. Kumar. Oh, I forgot to tell you. Remember, to go from here to the new system, this is the transform new system. To go from here to here. To go from the old system to the new system. This is the old system to the new system. We say we have the reordering algorithm. Reordering algorithm. Remember the one I say I curve? Remember the I curve? To get that information, we call it that have to use reordering algorithm. Now, in the US literature, this reorder algorithm, we have a lot of different algorithms. The one suggested by the Professor V.V. Kumar in the University of Minnesota, we call it Matis algorithm. Matis algorithm. In fact, if you have a computer laptop, you can do at home. You just Google search, just type Matis, M-E-T-I-S. That is one of the many algorithms. Okay? Like the other algorithm you may have is called nested dissection. Nested dissection algorithm. And then there's another algorithm we call ND. Then there's another algorithm, we call it minimum degree. Minimum degree algorithm. There's a lot of algorithms. And all of those algorithms, they will try to provide the mapping. All of those algorithms, they try to provide this information for you. Do you understand? Oh, there's one more thing I forgot. One more thing. After you get A star and B star, you can apply Cholesky, step 1, 2, 3, right? But at the end, what you get is this guy. You agree? But what you want is this guy. Do you agree with me? But if you get this guy using step 1, 2, 3, right? Can you go back to here? It's easy. You just go backward. Instead of going from old to new, now you want to go from new to old. Do you understand? Do you understand? And then you make use of the same information here. Like for example, suppose X star, okay, X star, let's say equal to 8, 5, 4, 1, 6.6, 2 point minus 2.2, something like that. Then, can this X also have 6 values, right? 1, 2, 3, 4, 5, 6 values, right? Can you tell me 6.6 will be in where here? Ah.
No.
This is the new location number 5. Right? This is the new location 5. So you say the new location 5 become the old location 2. So if you got the answer here 6.6, that will be in the second location here. It's very cheap, very easy. Okay? So let's try to summarize it. If I give you A, symmetric positive definite, I give you the right hand side vector B, and I ask you to solve for the X, what will be the step-by-step procedure? What is the first step you do? You will provide the non-zero location of the original matrix. Provide that information. Then this software, which is free, will give you iPerm. Alright? After you get iPerm, you transform A become A star. You transform B become B star. Okay? Then after that, what do? You apply Cholesky. Step 1, step 2, step 3. You obtain X star. And then after you get X star, you transform back. That is the procedure. Is that very clear? Yes. Okay. Now let me give you a real life engineering problem to show you the advantage of using the so-called reordering algorithm. Very big advantage. Let me try to show you. Oh, can somebody help me a little bit? You go back to the place that have all kind of page, 155, 75, maybe from this. Oh, let's go to 722. 722. Let me see. I don't know which one. Maybe 151. Yeah, click that one. I hope that's the right one. Yeah, this is the right one. So take a look on the page 151. Take a look on page 151. Page 151. You see, this is the finite element model of the car, right? Let me explain to you what's going on. Very important. You see, for this finite element model, do you know how many equations you have? 263,000 equations. What does that mean? This matrix A, it has 263,000 rows and 263,000 columns. It's a big matrix. Actually, for us, it's very small because we already solved the problem with 10 million equations. 10 million. Okay, so this is not big. But the important thing is, for this matrix, you see, let me see, where is that? You have 6,267,000. What does this number mean? Can somebody tell me? You have more than 6 million non-zero from the very beginning. Do you understand? Remember I told you NCOEF1 equal to 12? Remember the small example? We have 12 non-zero, and then we have 6 extra non-zero fill in. Remember that? So what does 12 mean? The number of non-zero you have from the beginning, before you do factorization. So for that big system, very big, right? You have about more than 6 million non-zero. Is that all right? Now, you apply reordering algorithm by Professor V.D. Kumar made this. Now, when you do step 1, step 2, step 3 of the new system, the total number of non-zero become what? More than 36 million. So what does this number represent? This number, 36 million, right? It is equal to 6 million non-zero that you have from the beginning, plus about 30 more million extra. That is because you already use his algorithm. If you do not use his algorithm, you just solve this guy immediately, This number, instead of 36, it may be more than 100 million. Do you understand what I'm saying? Suppose you apply step 1, step 2, step 3 directly on this system without using Bayes' reordering algorithm. This number, instead of 36 million, it becomes maybe more than 100 million, a lot more. And because you use the reordering, that's why this number becomes 36 million. It's still a lot bigger, right? But it is better than 100 million. Do you understand what I'm saying? Now, remember in America, they have a very famous statement, nothing is free. Remember, nothing is free. So, of course, when you do the reordering algorithm by Professor B.B. Kumar made this, you get to solve a new system. The advantage you got is the number of non-zero after you do factorization. Even though it is a lot bigger than before, in the beginning, but it is still not too bad. Because if you don't do it, it will be a lot worse. So you may say, okay, that's good. I use Professor V.D. Kumar reordering algorithm. I can save computer memory, save computer time. But how about the extra cost to use his algorithm? Do you agree? Do you understand or not? Because to use his algorithm, it's not free. It will cost you something. But the good news is this. Here's the good news. If you apply these algorithms, of course you have to spend some extra time. Let's say, well, actually, here, tell you, 42 seconds to do the reordering. This is the extra cost. Do you understand? The extra cost when you apply his algorithm. But, so this is what you waste, right? Extra. But when you solve the new system, you may save thousands of seconds. Do you understand? So my point is, to use his algorithm, it will cost you a little bit, but what you gain is very big. And that's why, in real life, nobody is stupid to solve the original system. Nobody do that. Everybody has to go through this. Now, in case some of you may have some experience about finite element software, like I think I talked to Dr. Do Bok Anh today. In the US, there's a lot of finite element software. In the US, there's a lot of finite element software, right? Like for example, the most famous one is Nastran. This is where I say very quick. Nastran, okay? ANSYS, okay? Abacus, a lot of SAP, SAP, SAP 2000 or whatever. Do you understand? They're all finite element software. Is that right? Yeah. But listen, every software here, they all depending on AX equal to B. So to solve this system, it will be, that is the main thing about all of those software. And if you look at the inside, I don't think you have a source code because it costs you a lot of money. But I can guarantee you, whoever wrote the software, they do this, they will go through the procedure that I just explained to you. Nobody will be stupid to write to solve directly to B. They always go through reordering first. Okay, so I'll let you know. Now, because I'm a little over time, okay, I just say maybe one more statement so that way you know what you are going to do the next step. So just give me 5 more minutes. Just 5 more minutes. By the way, if I go more than that, you remind me because I love to talk. Okay? 5 minutes. See, this is a very important big picture. When you solve ax equal to b, for the given a, the given b, and x. In the big picture, there's two categories, two different group of methods. First, we call direct method. Can you see all of them? Yes. Okay. Is it okay? Okay. Direct method. Direct method. Now, direct method consists of what? Oh, let's say like direct method like Cholesky. Okay. And they have L, D, L transpose. They have another method called LU. Now, what is the Cholesky method? What is the requirement? A has to be symmetric, positive, definite. You agree? And this one I already explained to you. Suppose you have a system equation A, where A is symmetric, but let's say negative definite, not positive. Negative definite. Negative definite. Of course, in that situation, you cannot apply Cholesky. You have to apply another algorithm we call LDL transpose. This algorithm is very similar, but right now I don't have the time. So I just want to let you know. Now, there's another algorithm called LU. L means lower triangular. U means upper triangle, remember? Now, this method will be used for what situation? When the matrix A is unsymmetric. When A is unsymmetric. Do you understand? So, that's why when the people say, hey, Professor Nguyen, I have a matrix A, I have a vector B. Can you tell me what algorithm I should use? I have to ask him, well, in order for me to answer, you have to tell me, what is your matrix? What is the characteristic of your matrix? If he say, well, my matrix is symmetric, positive, definite, then I say, okay, we'll use Cholesky. If your matrix is negative, definite, I can use this one. Oh, by the way, the LDL transpose algorithm, it can handle both negative as well as positive. So this is more general. Do you understand? Now, let me ask you this. Between these two, remember, LDL transpose method can handle both negative and positive, okay? Can you tell me which method costs more? I give you a hint. Cholesky only can solve positive matrix, positive definite. LDL transpose can solve negative and positive. Which method costs more?
The second one.
Of course, you get what you pay. If your method is more general, of course it will cost more. Well, is that right? So, but the good news is, this method may be 5% more expensive than the Cholesky. That's why I prefer to use this method. So that way, I don't have to worry, is that matrix positive or negative? Right? Because it costs just a little bit extra, 5%, not much. So I usually prefer this one. Okay? Now, but if your matrix is unsymmetrical, then you cannot apply this. You have to apply LU algorithm. You understand? Now, so for now, I just temporarily stop in here. But in the next meeting, see all of those methods, they call direct method. In the next meeting, we'll talk about iterative method. Iterative method. They have a lot of algorithms. Like for example, conjugate gradient. Conjugate gradient method, which is called CG. This is the iterative method. borrow from optimization idea. Okay? And then they have a lot of methods. So, let me tell you, in this method, direct method, right? What is the good news and what is the bad news? The good news about this method is what? No guessing. You give me the matrix A, you give me the vector B, I guarantee you, I give you the correct answer. I don't have to guess. So that is the good news. And the answer is guaranteed accurate. What is the bad news about this method? Non-zero filling term. That is the bad news. Even though we use Professor V.V. Kumar matrix, remember, reordering? The numbers still grow a lot. That is the bad news about any of this method. Now, in the next lecture meeting, I will talk to you about those things, right? Belong to iterative. Again, it also has some good thing, it also has some bad thing. Very easy to remember. The good thing about this guy become the bad thing about this guy. The bad thing about this guy will become the good thing of this guy. Like for example, what is the bad thing about this guy? Can you tell me again? What is the bad thing about this method? Non-zero filling term. In this method, it is very good. Why? The number of non-zero filling term is 0. In other words, whatever the non-zero you have at the beginning, that's it. Not increase anything. It's very important. So like for example, in the beginning, if I have 6 million non-zero, right? If I use this kind of method, still 6 million. So that's very good news. What is the bad news? Remember, what is the good thing about this guy? Very accurate, remember? Very reliable, no guessing. That becomes bad thing about this guy. Why? Any of this method will require you to have a guess solution. Guess solution. You guess the solution. And then you do through iteratively. Keep improving until, how do you know when to stop? Until you feel that you get enough accuracy, then you stop. So, there's some good, some bad. There's some good, some bad. After you understand these things, which I hope I have time next time, then the last thing I'll talk to you, maybe in here, or maybe I'm